Spencer Rice, Alan Turing, y lo que los nombres de las aulas, estos Gottesland, Leibniz,
Doy clases a una universidad que un aula se llama Satoshi Nakamoto.
¿Tú no vas a clase en la UBA?
También, pero en la privada
Aparte vas a una clase.
hizo todo. Imagínate que un aula se llama Satoshi Nakamoto.
Pero acá está las calles.
So, good morning everyone. Today, this section or the day will be devoted to probability. Because you know, our workshop is concerned with logic and reasoning and probability. And we are trying to put everything together. They are the three sides of the same coin. If a coin has two sides. And Professor Julie Stern will be speaking today about this chance and complementarity, analogy and prototype, homology and archetype as source of knowledge. In a nutshell, this is about the following, about how we need to use the discrete probability and continuous probability, am I right?
Yes.
In the same way, I mean, on both together, neither alone is sufficient to take care of the beautiful task of reasoning in the world. Professor Julie Stern is a professor of the University of São Paulo, Department of Mathematics and Statistics.
Applied Mathematics.
Applied Mathematics, because there are several departments there. He's a physicist, please correct me.
Yes.
He's originally a physicist, studied mathematics and several topics of discrete mathematics.
What?
Yeah.
I study a lot.
And now he's a very good statistician with lots of work in industry and companies and academic work as well. And now he's much more interested in the connection between logic and probability.
That's right.
And a bit of philosophy in the middle. And so I will give back the word to Professor Stern.
Thank you very much. Thank you all for being here. So the title of this presentation is Chance and Complementarity, Analogy and Prototype, Homology and Archetype as Sources of Knowledge. Analogy and homology are very basic tools used by biologists. And I'm going to try to look at those tools and see how they are well used and how they are many times misused. And one of the, well, there are logical and statistical fallacies that go into the misuse of these concepts. And one important misuse is to mix and match carelessly discrete and continuous probability. That's important for the topics we are discussing. And I will argue that homology has essentially to do with discrete probability. And analogy has essentially to do with continuous probability. And you have to use the right tool for the right job. Like what was the engineer of Enterprise, Starship Enterprise?
That's what Henry Ford was.
Yeah, he has to use the right tool for the right job.
Yeah, you cannot
Or the right tool for the job, I don't know. But continuous probability is the tool for analogy, and discrete probability is the tool for homology. That's the core message, at least for this audience. And so, yeah. Por favor, não lembra se eu esqueci. So, kick up abstract of this presentation. I will talk about key concepts of probability, organism, purpose, and evolution. There is always a topic and a subtopic. In the time I have, I hope be able to talk about the topics, but I will have to skip the subtopics. So, number 2 topic are those basic concepts. And there is a subtopic about how to understand probability as a convexification, deconvexification operator. Convex spaces are of course continuous spaces, and discrete spaces are strictly non-convex. And one way to look at probability is an operator that can take you from a convex space to a discrete space and vice versa. And that's, I think, a very nice way of looking at probability, not explored so far. Then I will look at homology and archetype and see why discrete probability is the right tool to deal with problems of homology and archetype. Then I will explain the concept of analogy and prototype and tell you why continuous probability are the right tool to deal with problems of analogy and prototype. Teleology and fine tuning, that's conditions for a good analogy. And then I will show you several fallacies that are prevalent in the biology literature, really prevalent in the biology literature of those people invented those concepts and then they misuse it all the time.
That they use in medicine?
Yeah, that too.
That will be done.
Okay, and at the end I will study in detail a case study that is the symbolic language of the honeybees. We will try to analyze in which sense honeybees have a symbolic language, and the last topic is to see, well, I will argue that they do have a symbolic language, but of course we also have to contrast with human language. In which sense innovation and conscience are different for the honeybees and for humans. And then finally, what we do that they don't do, that's metaphysics. Giving causal explanations about the world. That's our unique thing, Aliwar. So, probability or chance have a long history in the scientific literature in the Western world. It begins, like everything else, with Aristotle. Aristotle talks about chance in physics, in his book of physics, and his book of zoology, part of animals. In physics, he says chance is a concept that has no value, period. Forget about it.
Forget about quantum mechanics.
Forget about quantum mechanics. But in part of animals, he says not. He says absence of haphazardness that can be understood as non-involving chance or improbability. I read it as improbability, and I will argue later on that improbability is a key concept for understanding what's going on in biology. And conductiveness of everything to an end, that is teleology, are the keys to understand biology. And I completely agree with it. Where you see improbability and teleology, that is where you find virtue, kalos, beauty, virtus, good in the world of zoology. And I think he nailed it. But probability took a long time to enter the world of science. Nowadays we all talk about quantum mechanics, but the first theory that used probability in an essential way was the theory of evolution of Charles Darwin. That there, for the first time, probability, stochastic events, stochastic processes are a key driver of what's going on. And
this will continue going to the field. Because from the discrete point of view, people say about the Fermat letter, about the game and this kind of thing.
Yeah, for gaming, but I'm not sure if gaming is science.
Game is not.
I don't know. But biology is science.
Okay.
And the theory of evolution tries to explain what's going on in biology. And I think the best summary of how exactly probability enters the theory of Darwinian theory of probability can be found in a letter of Darwin to Charles Lyell that has a paragraph that goes like that. The view that each variation has been providentially arranged seems to make natural selection entirely superfluous, and indeed takes the whole case of appearance of new species out of the range of science. So if we have to treat it as science, then probability has to be at the core of it. It seems to me that variations in the wild and domestic conditions are due to unknown causes and are without purpose and insofar accidental. That's one of Darwin's two dices, in the words of Johnson. He says that Darwin uses two dices. The first dice is this one, fortuitous variations. Variations occur, mutations occur without purpose, or at least we don't know. And in that sense, for us, they are accidental. And second, the second dice is likelihood of survival. And that they become purposeful only when they are selected by man for his pleasure, or by we call natural selection. Then a second way in which probability works is by selecting what's good. It's also a random process, but it's a random process with a bias to select the most useful or the best adapted variations. And then he ends up saying that I do not wish to say that God did not foresee everything which would ensue, but here comes very nearly to the same sort of wretched imbroglio as between free will and preordained necessity. So he sees there is some very deep conceptual problems in this theory, but anyway, and he is not sure that he can solve all those metaphysical problems, but we don't care. We are going to use our two dice to understand how species evolve. And how do we describe the evolution of species, the evolution of the zoological world, of the botanical world? The best way to describe this process is in a tree of life. The tree of life is a concept that has been evolving sometime before Darwin, and that he uses in a modified way. So these are some of the pictures of tree of life, some at time a century before Darwin and 2 centuries after Darwin. We start with the first figure to the left with a family tree of species. Like we are, oops, that. With a family tree of species. Species are somehow related, but there is no evolution going on, no transformation going on. We are just relating the species by their familiarity, by familiar resemblance. So that's a family tree as drawn by Augustin Augier. Then we have another tree drawn by Lamarck, Jean-Baptiste Lamarck, where he introduces the concept of transformation of species. And it's a process not driven by random processes, but by, Lamarckian processes. I don't have time to go into it. finally, not finally, the third figure is a sketch in Darwin's book note of 1837. It takes a long time for him to publish his results, only in 1859 he published, but that's the first time where he draws a tree of life, and we have a transformation process like in Lamarckian theory, but that's driven by random mutation or random change. And finally, a contemporary tree of life, where in parallel to random mutations you have crossovers and inbreedings and parallel gene transfers and other complicated stuff. Huh? Anyway, this picture, the tree of life, is like the coagulated past, the discrete event history of what happened. Huh? The best way to describe it is a statement of William Lawrence Bragg. Of course, he was talking about something else. He was talking about quantum mechanics. But for me, it's the best description of what's going on with those three, with this, when we see a picture of a tree of life. He says, the moment of now is like a sieve passing steadily through time. In front there is a probability future, a continuous wavy future, if you like, in which we can predict only how likely some result is to happen. At times streams through our sieve, it coagulates this wavy future into a discrete particle past, where the precise history of events is recorded. So the tree of life is the recording of those discrete events. They have to be discrete. When something happens, it happens in discrete space. Right? But if you look at the future, it's a continuous space. So for the first time, we see that continuous spaces and discrete spaces both have their place, and we have to keep them both. Focus of this article: biological evolution theory, the nature of random causes, and improbability as an indicator of many things. Improbability, in Aristotle's words, non-haphazardness, is an indicator of identity. When I say in biology, my arm is like the wing of a bat, or like the forearm of a mole, or like the flipper of a whale, they are all the same organ. In which sense can I say it's the same thing? How can I identify those things? The identification is made to this concept of homology, and the way to check that the homology is a good homology, that the identification is true, is by an argument of improbability. Teleology and in the same way, I say that my eye and the eye of an octopus are both the same thing, in the sense that I use the same word eye for both organs. But they are not homologous organs. They are analogous organs. And the key to build analogy and to check analogy is continuous probability models. Homology has to do with discrete probability, analogy has to do with continuous probability. And the argument of improbability is a bit different. In discrete spaces, improbability means small but finite probabilities, of course. It's only one or a few possible arrangements within a large sort of arrangement. Small but not null probability. In continuous probability, what I will define as fine-tuning conditions are zero probability. So what we witness is an event that has zero probability happening. A miracle. That's a miracle. Well, that's the definition of a miracle. It's my definition of a miracle. If you see something that has zero probability, it's a miracle. Well, miracles happen in science all the time. Non-believers at USP are required to take physics laboratory 101, 102, 103, 104, where they will experience the miracles happening described by Newton's law, and you check that Newton's law is a very good theory, something that has zero probability of witnessing an event that's fit exactly that law of motion happen all the time, and you can check it in the lab and see that it works. And the key to deal with those phenomena, check those phenomena, are continuous probability models.
So you mean that miracles don't occur by discrete probability?
They are small miracles. Miracles that don't imply zero probability, that imply very small probability. But true miracles, those are in the continuum. Their probability is zero or infinitesimal. But one way or the other is they're continuous. Whatever your model for the continuous is, they are zero probability or infinitesimal probabilities. Oh, that's the story about probability as a convexification or deconvexification operator. 2 hours is too little, I have to skip that. So, here we have a tree of life, or 2 depictions of a tree of life. I don't have time to go into details on why those 2 are interesting. They are tree of lives. The key question is, how do we reassemble a tree of life? How do we? It's a puzzle, right? We are now at the moment of now, we only have access to this top cross section of the tree of life. How we reconstruct the tree of life in the past. That's one of the key problems of biologists. Biologists are all over this problem. It's essential part of their lives, reconstructing tree of lives. How do we do that? Well, from the very early stages, they recognize there is one tool that's very useful to do that. That has to do with homology. Homology is a concept invented by this guy here, the first one. Those are my heroes of this presentation. Like Villa Cesar, do you see Villa Cesar? Hero. Starts with the heroes of the chapter. The heroes of this chapter, of this presentation are Richard Owen. The date here is the date of birth of each one, not of life birth, but intellectual birth is the date of the first publication of the guy that I cite in the presentation. So, Richard Owen, 1832, Charles Darwin, 1859, Konrad Lorenz, 1932, Carl von Frisch, 1923. Those 2 are ethologists, and they were the first guys to use this concept of homology and analogy in the field of ethology and behavioral sciences. And the guy, and the last guy here is Johannes Kepler, that we will see was speaking about archetypes long time before. So, what's homology? Homology has to do with this. You see these 4 examples of arms, of 4 limbs. The wing of a bat, the flipper of a whale, the forelimb of a mole, topeira. In Portuguese, he uses arm to dig. Huh?
Kind of gopher.
Topeira. Huh? And the arm of a man that we use our heads to find manipulation. The function of those 4 members are completely different. Their form is completely different. But if you look at the bones, they are the same bones. Each bone is different. Ones are very small, ones are thin, ones are thick. But what's the same here? The interconnection diagram, the topological map. So in this sense, they are the same. This is the concept of homology. Those 2 organs or 2 machines or 2 structures, they have the same or very similar topological maps or connection diagrams. Yeah? And biologists found out that homology is the key structure to trace the evolution of species. Yeah? The definite word, the final word in the concept of homology was written by a guy called Alfred Remane in 1952. He worked in Germany. I think the German edition is a few years earlier, but he identified homology as used by biology with homology as used in topology, and gave a very mathematical and abstract treatment to this concept. And here you have beautiful diagrams from the book of Remane showing how topological structures can evolve and modify in a very abstract way. Beautiful. There is a lot to say about these diagrams, but again, I have too much thing to do today. Of course, I have to go a little bit faster. And here is an example of how we use, not we because I'm not a biologist, but like biologists use this concept of homology to trace and to reconstruct family trees of species along the time. Wings of insects are structures that fossilize very well, and we have fossil records for insect wings going a long time into the past. And the nerve structure of those wings are very rich topological structures. And we can look at them and clearly follow how they evolve, and from that we can reconstruct the family tree or the evolutionary tree of insects. And that's a piece of family tree of insects showing how Diptera evolved from Lepidoptera. Don't ask me what those things are because I have no idea. But the diagrams are beautiful, right? So, Richard Owen defines homolog as the same organ in different animals under every variety of form and function. These relations, homology, are mainly, if not wholly determined by the relative position and connection of the parts, and may exist independently of form, proportion, substance, function, and similarity of development. Archetype is a Greek word that Owen uses. He says the original meaning of the word in Greek philosophy comes from arche, the origin, and typos, type, the original of that which is represented in a picture of a statue. In the language of Plato, it means the world as it existed before creation in the mind of God. So the structural archetype, the abstract structure of it. Archetype in anatomy is how he is using this concept, is that ideal or fundamental pattern on which a natural group of animal or systems of organs has been constructed, and to modifications of which the various forms of such animals or organs may be referred. The archetypal figure has been most clearly recognized in the study and modification of the skeleton of vertebrate animals. So it's important to realize that Owen invented this idea of archetype and homology before Darwin, before the theory of evolution. For him, it has nothing to do with evolution, of course. It was before the evolution. But he saw how it was the key to relate different species. That's how I'm using the concept of homology in this article, very close to Owen's use. You see, my definition of analogy will not be that close to the definition that biology is, but in this case, very close. So a structural archetype is a schematic plan or a topological map characterizing the structure of a complex system, organism, or organs thereof, by the layout of organization from constituent parts or by the interconnection plan of its basic components. Homologs are distinct organisms or organs thereof described by the same or similar structural archetypes. Homologous systems may have different shapes, sizes, functions, construction, genesis, material implementations, etc. Homology may be used to establish identity, in practice, use of the same name of corresponding parts in different systems, or animals, or organs. In the context of modern theories of biological evolution, homology may be a useful tool for investigating and tracing phylogenetic paths of gradual development diverging from a common ancestor, root in the branching, in a branching process of a tree. And the key to check for homologies are improbability arguments. Owen never really talks about improbability arguments, but I can try to extract by forceps some improbability argument from Owen's writings. I found an obscure passage of Owen's writing. He writes a lot, so it's easy to find what. He says, these structures he's describing, several structures, are too numerous and irregular in their shape to allow for a moment the supposition of their being accidental. So he has this idea of improbability argument in his mind, although he never uses it for anything. But he's my hero of this presentation. I'm trying to give him credit. At least in some form of implicit argumentation for improbability. Yeah? And I will skip the middle one and tell you, read the last citation here from Conrad Lorenz in a paper of 1981. The probability of two forms of life evolving by sheer coincidence a certain number of identical characteristics can be calculated. It is equal to 1 over 2 elevated over 2 to the power n minus 1, and in the number of similar of identical characteristics. He tries to quantify the argument of improbability. He makes a very poor job in this quantification. It's a kindergarten argument. It's a kindergarten calculation, but it's okay for a biologist, right? Yeah? He writes an equation. He writes a formula.
Can you imagine that? Two species with 11 characteristics, right? 11 similar characteristics, would have a chance of 1 over 1,000 normal chance of being developed by sheer coincidence.
Yeah, that's a. But if you want to see good arguments of this type, read a book of Joseph Feldstein, Inferring Phylogenesis. This guy uses this kind of calculations of arguments of improbability to follow phylogenetic trees in biology and also in the field of historical linguistics. And in the reference you also find a work of Raphael Stern, my son. He did his PhD in historical linguistics and has some very powerful algorithms to compute this kind of branching process, compute the probability or improbability of processes in this kind of stochastic process. So much for homology. But that's not the only context in which we say that two things are the same in biology. As I told you, I use the word eye for my eye and for the eye of an octopus. If you look at the eye of an octopus and to the human eye, you immediately come to the conclusion both animals use this organ to see. They have the same function. So they are the same. I'm justified to use the word eye for those two things. And if you want to build, when you want to build an argument based on homology, it completely fails. You see that those organs are not homologous at all.
Why?
Why? Because here at the right you have the embryological development of the eye of a cephalopod and the eye of a vertebrate. And you see that the different parts of the eye come from completely different tissues. They are interconnected in completely different ways. they work in some sense in the same way, but in other senses in a completely different way. For example, the human eye has a lens that has a fixed position and a variable geometry. And the octopus has a lens that has a fixed geometry and a variable position. They're completely different organs from an homology point of view. But they kind of work the same. How is it that they kind of work the same? And who asked why? As a complement to the answer to your question, here you see the cephalopods and vertebrates are very far away in the tree of life. So those structures cannot possibly have evolved from the same animal or have the same origin.
I understand that the function is similar, but the structure is not.
Exactly. So they are not analogous. What is similar is the function. And how I describe the function. I told you how to describe structure and by an archetype and how to relate archetypes or different organs to a same archetype, and in this way build an argument of homology. But what about function? Let's see. So, again, in more detail, the structural diagram of the two eyes of an octopus and of a human. You see the interconnection diagram is completely different, the tissues are completely different, the lenses are built in completely different ways, the innervation of the retina is completely different. By the way, the octopus eye is much better than the human eye. Human eye has a lousy engineering process. Octopus are much smarter than this.
That's what mine doing that.
So, Owen defines analogy as follows. Analog, it's in a dictionary, in a glossary of poets words. Analog, a part of organ of one animal which has the same function as another part or organ of a different animal. And he says, but homologous parts may be and often are also analogous parts in a fuller sense, vis-a-vis as they performing the same function. They are homologous in as much as they are composed by the same answerable parts, and they are analogous of each other in as much as they have the same relation of subserviency to a function. To what?
Like.
Puta, nós. No? So, have to read it again or? No? So it's very important to realize that for Owen distinguished two kinds of resemblance in the corresponding organs of parts of bodies of different animals. One, essential structure agreements relating particularly to relative positions and connections. That's homology. And second, similarities in function or use that the organism makes of this part. They are really different qualities and have no necessary dependence upon each other. This is a quotation that I take from an article of Boring. Two different things. Okay, so how do I characterize analogy? Owen is my hero, but he stopped short of giving a good, precise characterization of analogy. He does it very well so for homology, but he doesn't go far enough for analogy. He says the same function, and that should be enough. For the biology, that's usually enough. The biology know what an organ is used for. It's obvious. But I'm a physicist, I'm not a biologist. What's obvious for them is not obvious for me. So I want a better and more formal characterization of analogy. Again, I'm going to extract by forceps a characterization of analogy from the writings of Owen. Even if I fully recognize this, I'm using a forceps to take this definition out of his writing. He compares the flicker of a whale and a fish, and he also compares, he said they are analogous, the eye of a nautilus, cephalopod, and the human eye. He says, in the nautilus, that's this creature here, the eye presents the simplest condition of an organ of vision, consisting only of a darkened globular cavity or a camera obscura, in which light has admitted by a single orifice and a nerve expanded at the opposite side to receive the impression. So he compares the eye of the nautilus and the human eye not directly to each other, but he uses the resources to compare in both to a camera obscura. Camera obscura is the word camera obscura is used for the first time by Kepler in 1604, and then again in 1611. In 1604, Kepler describes a camera obscura like the Nautilus, a room with a small hole in the wall, and in 1611 he describes a camera obscura like this photographic camera here, where there is a lens. By the way, Kepler is the first guy to give us a description of how a lens works. Thin spherical lens. The first guy to give a mathematical description of a lens is my forever hero, Mr. Johannes Kepler. And in Kepler's description of a lens and a camera obscura, he ends up giving this equation, the equation of how a thin lens works. And if you want to build a camera obscura, a camera obscura is in focus if the distance, the focal distance of the lens, the distance of the lens to the plate or to the retina on one side, and the distance from the lens to the object are in this relation here. This relation is called the focus equation.
Excuse me, there must be a miracle because the sum turned into a minor.
What? Well,
Just joking. I mean, there's a plus sign. Then it turned to be a minus sign. Miracles happens.
well, there is a wrong sign somewhere. Okay? But there is a miracle. If you see a in focus camera, there is a real miracle there, and the miracle is in red. Is the equality sign. Huh? Precise focus is a miracle. It's a continuous equation, so it's really in focus. It's a miracle.
turns out to be a zero.
It's a zero probability. And that is the anchor. That is the way to anchor an analogy argument. It's my take on this problem. Yeah? And here you have, if you don't remember the focus equation, there is a beautiful book wrote by Fuller, physics including human applications. Is a beautiful book of physics for biologists. And the book that I used to study in high school of physics is the PSSC physics curriculum. That's a basic book for high school physics that was translated to Portuguese, to Spanish, and to all languages that know in the world by the now extinct USAID. My thanks to USAID. They gave me beautiful books when I was at college. Not only the book, but laboratory kits and all that was a beautiful gift from USAID. So, Owen says, adaptation to a special end are made comprehensible on a higher principle, and a final purpose is gained in the relation to human intelligence in the instances where the analogy of a humanly invented machine explains the structure of the divinely created order. So that's the statement that I found and run with it and use it to build this, to use this criteria for a good analogy argument. Also, of course, he speaks about divinely created organ. Some people may object to this divinely created organ. How do I understand this divinely? Well, you can replace divinely by nature in a way of Spinoza, Deus natura, or the evolutionary process, the unfolding evolutionary process. But anyway, the one who created a miracle, because it is precisely a fine-tuned machine, or a fine-tuned organ that I can understand by comparison to a fine-tuned machine that I created. I know how it works. So I'm using Owen never defined it, the biologists never defined it, but I'm defining prototype as an analogous to the concept of archetype. A functional prototype, a functional prototype in blue, because it's a new concept, it's a concept that you not find in the book of biology. A functional prototype is a human invented machine or method, a proof of principle device, a proof of concept model, demonstrating key functional aspect of a system conceived or built to achieve a certain aim or to serve a specific purpose. A fine-tuning condition is a prototype's configuration or setup well calibrated or precisely adjusted for its aim and purpose. In the example that I gave is the focal equation. Analogous to distinct organisms, organs, or part thereof, explained by the same or similar functional prototypes. Analogous systems may have different structures, shapes, sizes, construction, genesis, material implementations, etc., as long as they have the same function. Analogy may be used to establish identity, for example, using the same name for corresponding part in different systems. In the context of theory for biological evolution, analogy may be a useful tool for investigating and tracing distinct phylogenetic paths of development converging to a similar solution. So my eye and the eye of the octopus don't have the same origin, but they converge to a similar solution. What solution? Kepler solution. A câmara obscura obey the focal equation. Everything is clear?
It is.
Well, do you bought the fish I'm selling?
Yeah. For the moment.
For the moment, okay. Well, discussion of analogy may get more complicated. I also call the eye of a bee an eye, and that it works in a different way. How can I extend the concept of analogy to cover those cases? I have to skip that. My favorite eye, the eye of a lobster, that works in a completely different way. Isn't that a beautiful eye? No? When you understand how this thing works, you find that the eye of the lobster the most beautiful eye you ever saw. I'm showing you that's the eye of an insect, very different principle, and here the eye of a lobster. The lens of the lobster is not a lens at all, it's a collimator, it's a spherical collimator. People didn't understand how this thing worked until the 20th century, the late 20th century. It's amazing. Well, anyway. But one thing that requires further discussion is that idea of function. Function has to do with teleology, right? What for? Is it synchronized? Yeah. How can I say that someone is doing something with some purpose? Huh? Here is an Indian, Brazilian Indian, fishing with bow and arrow. I look at him and I'm sure that he's fishing. The aim of this, the purpose of this shooting the arrow is to catch a fish. How can I be sure of that? Well, with the Indian I can go and speak to him. Maybe I have to learn Guarani or Tupi, but I can go there and ask him, but why are you doing this? And he will answer me, idiot, I'm trying to catch a fish from the sea. That's it. But in the second figure I have the reverse situation. A fish, an Australian fish, shooting. Australia has some weird animals. Shooting spitting a drop of water to hit an insect on a leaf and eat the insect. He's fishing too, right? Or he's reverse fishing. But how can I be sure? I cannot ask the fish. And in the last figure, both the Indian and the fish have to account for the difference in diffraction rate of water and air. They have to correct the angle of the shooting to this according to the diffraction, to Snell Descartes' diffraction law, right? And the last figure is a light ray obey the same law, Snell-Descartes' diffraction law. What for? What's the purpose of the beam of light in following this path? The beam of light is trying to minimize the time travel. It has a goal too. Ask the beam of light. Ask the photon.
Where does it want to go? Where does it want to go?
The photon will tell you. I'm following Fermat's principle. I'm trying to minimize my time travel.
I guess Noether's principle.
Yes, ultimately that's Noether principle. Yeah. Noether is the key explanation of everything in physics, right? Is the final anchor of everything in physics. Okay. And well, all those cases are studied in detail in this article that I published in Principia. But not to repeat the same case, today I'm going to study a different case. The construction, how do honeybees construct the honeycombs. You could build a honeycomb using hexagonal cells with a flat bottom, right? And that would require some amount of wax to store a given amount of honey. But if you tilt the bases of the honeycombs, so to make it not flat, not a cylinder, but a pyramidal, to give it a pyramidal tip, you can optimize the amount of honey that you can store using a given amount of wax to build the honeycombs all the way around. And you can use simple calculus to compute the angle, or the same thing, the relation between the side of this facet and the diameter. And it happens that the relation happens to be square root of 2 over 1. And I tell you, the honeybees know what they are doing. They are building the honeycomb this way with the purpose of maximizing the storage. And how can I attribute purpose to the honeybee? Look at it. It's a miracle. And either it's an unexplainable miracle, a true miracle, square root of 2, and I can measure it with the precision of my instrument is square root of 2, or they have this purpose. I was going to end the statement with this purpose in mind, but I will not end the statement. I will keep the in mind of. I will stop with this purpose. How do I justify a teleological argument? Is by this fine-tuning, with this fine-tuning condition. There is an equation, some variables in the environment, and I'm taking an action given the environment described by an equation. In the case of the honeybees, the relation to that relation of the angles in the pyramidal tip has to be square root of 2 precisely. That is the first equality sign here, anchors in red. And the probability in the space of actions of that happening is 0. 0 is in blue here, is my witness, the miracle witness. Instead of miracle witness, I prefer the expression zero probability paradox. What the probability of that happening is 0, and why it's a paradox? Because in one way or another, I will give strong support, strong empirical support of that event with zero probability to happen. I'm going to tell you, look, I can compute a measure of evidence that tells you, yeah, that's really what's going on. We have a statistical apparatus that can be used to give you strong support for that statement that has zero probability. So I'm giving you strong support for a zero probability statement. That's the zero probability paradox or zero probability argument. That is the anchor to support teleological arguments, teleological statements, and analogy arguments. Because analogy, the way I build it, the concept, following Owen, has all to do with function and teleology and purpose. Okay?
But perhaps the surprise we have is because it's zero probability. It comes from the zero from measure theory. Perhaps measure theory is not so good. Like it gives rise to Banach-Tarski paradox, for instance, or this kind of paradox that I mentioned. So perhaps the problem is measure theory, that it's zero. And we regard this as a paradox, but it's not. Not any contradiction there.
Well, see, measure theory was created by Borel, by Lebesgue, to take care of probability under these conditions. The scientific community was claiming we have to use continuous probability, we want to use Kolmogorov axiomatization, and when we compute integrals, we are plagued by many contradictions.
Yeah.
Please give us a theory that teaches that accommodates us. And Borel and Lebesgue and those guys in France did the best they could. It's a pretty good job. The more I learn measure theory, the more I realize they did a pretty good job. It's not a perfect job, or other way to state it, the world is not a perfect world. It's a bit more complicated than I wish it were. But what's the best job that they could possibly? You can say, well, you see, if you replace the axiom of choice with the axiom of disability, then every set is measurable, and we are done. Yes, but then I don't know how to do anything in mathematics, because I don't know if it's some bad habit that I took along the way. But nowadays I use the axiom of choice every 5 seconds without even realizing that I'm using it. If I really want to replace in my life the axiom of choice by something else, it's very, very, I think only being born again, because other than that I cannot do it. Are there alternatives to Lebesgue measure theory? Yes, they are. I much prefer hard measure than Lebesgue measure. If I were to teach a course in measure theory, I would use hard integration. That's a lot simpler to define, but they're basically equivalent. You still have non-measurable sets and all those phenomena.
Equivalent for integrals.
Yeah, actually hard interval is a little bit more powerful, but
There's a question there.
oh, please.
Professor Giulio, in continuous probability distributions, we can avoid zero measures by working with intervals. And every empirical measurement has finite precision, so science is always working with finite intervals. And it is likely that fitness functions in evolutionary biology are also defined in terms of intervals because the world is kind of vague and kind of noisy.
Every measurement has a finite precision, right? But the laws that you are stating, that are the basis for your thinking, for your conceptual thinking, those are equations, true equations. The ideal in your mind are equations. And the sets described by these equations are truly zero measure sets. Of course, pragmatically, every measure has a finite precision, but everything has its place. Your measurements have a finite precision. Your ideal statement, the laws that you are stating, and the same way I can only really think mathematics using the axiom of choice. The only way I can think physics is with equations. I cannot think about physics using interval equations. I have to think about Newton's equation, Schwarzschild equation, Maxwell equation, Schrödinger equation. Those are equations. There are two equations.
Okay.
Right. The theory is equations, as you say. Of course, the models you use when you're actually doing experiments are going to be idealization approximations.
Yes.
But that's just because you kind of have to do that. This is why all models are false, but that doesn't mean all theories are false. This is what we were talking about yesterday. Theories are true. I mean, Newton's theory, at least we thought it was true. Einstein's theory, let's say we now think is true. The models of the theory, when we're actually predicting things, that's approximation. But that's because modeling always involves approximation. But you don't want to confuse that with what we think reality is like. This is back to your question about realism. No, of course you should be a realist about the theory. All models are false, but that's true in every science because you have to do approximation to do anything in a laboratory or do any real experiment. But that's you gotta distinguish the theories from the models of the theory.
Well, yeah, there's a good chance that reality itself is not continuous.
Okay, but that's a separate discussion to have. Even if it is, the models will be discretized anyway. So you still have to distinguish the theory from the models.
Yeah, that's right.
Yeah.
But I have to tell that modern science starts with continuous theories. Huh?
Yes.
Kepler is the watershed, and Newton is the real start of modern science, and he does it with the language of calculus. That's the language that we invented to treat continuous, the continuous. So modern science starts when we have the language to deal with the continuous. And if you want to understand modern science, you better come to peace with continuous mathematics.
Oh yeah.
And that is one reason why logic and statistics never meet. Because statisticians always do their models using continuous mathematics. And logicians, many of them, not all of them, but many of them are allergic to continuous mathematics.
Yeah.
And that cannot prevail.
Yeah. I mean, even quantum mechanics, the Schrödinger equation, there's nothing more continuous than that. So, yeah, you got to be careful. Just even if it turns out space-time is discrete, that doesn't mean the laws are discrete, because the Schrödinger equation is very much not discrete.
If I can complement something, continuous functions are the limit you get when you make intervals smaller and smaller. So they are very good approximations. even if the world is fundamentally discrete, and even if the Schrodinger equation, which is continuous on the time variable, even if time is discrete, you're gonna get a pretty good approximation by supposing that it is continuous. But we don't have to accept that.
No,
That
we
it's
don't have to
literally
accept
true.
anything.
No, you don't have to. You could be a nominalist, as we were saying yesterday. You could just.
It's a free country.
You could be a nominalist about the right. You can be a nominalist about the theories, but you have to be careful. Just because the models are always false, that's no reason to be a nominalist, because the models of every theory are false. Because in real life, you have to use approximation. So you have to be very careful. That inference proves too much.
Yeah, go teach physics without continuous mathematics.
It's just more
Try.
complicated.
No, it's
No.
impossible. Didactically, it's impossible. I argue. Didactically, it's impossible. First, you have to learn the theory using continuous mathematics. Then you can go to this kind of reasoning that you are doing.
For sure.
It's a very fine elaboration. It's a cherry on the top of the cake. Opa, mais uma? Dá tempo? Mais uma pergunta?
Maybe it's because the way you see it, I don't know, but you see as points, right? But it's still continuous under Lebesgue measure theory, the Lebesgue measure in this case. So maybe it's that.
So could you please rephrase? Sorry.
I mean, you see it like a set of points, right, in evolution, maybe. I don't know. I'm not sure that part is correct. But if you see it as in a measure space and you apply Lebesgue to it, you can calculate it as continuous space. So it's kind of continuous, but it's just a conceptualization. But you can see it as discrete because it's points, but it's actually continuous.
Yeah, I guess that's.
So let's make a break.
We'll have a quick break now, and let's thank Julius. lecture, part 2.
Okay, now I will show you many instances of logical and statistical fallacies that appear in the biological literature using those concepts of homology and analogy. First, the logical fallacies. Logical fallacies that have to do with fallacies that you know from day one you enter here at Clay. Two of them, they all have to do with swapping the role of variables. One of them, classical one, affirming a consequence of converse error, having A imply B, having B and concluding A fallacy, classical fallacy. Second fallacy, affirming a disjunct mutual exclusion error. From A or B and A conclude not B. Before we see what modern biologists do wrong, let's see what Darwin and Owen did right. So what did Darwin himself said about homology and archetype? He said, the homological construction of the whole frame in the members of the same class is intelligible if we admit the descent of a common progenitor. So he's saying homology is a very good tool to trace common descent. Well, the second quotation says something very similar. I change here, I wanted to change there. Oops. Okay. And now, see. But one of the best friends of Darwin theory of evolution, a guy that was trying to help Darwin the best he can, was this guy Edwin Lancaster. And then we have a Portuguese saying, Deus me ajude com meus amigos, né? God help me with my friends. See what Lancaster said. Structures which are genetically related insofar they have a single representative in a common ancestor may be called homologous. So inverted the implication. He's now defining homology by common descent. He completely inverted the sign of implication, and by so doing did homology a useless tool. Yeah? Lawrence, one of my heroes and a Nobel Prize in biology, does the same mistake. Look what he says. The concept of analogy in the course of evolution, it constantly happened that independent of each other, two different forms of life take similar or parallel paths in adapting themselves to the same external circumstance. That's called analogy. He inverts the sign of application. For analogy. Analogy, we speak of analogy in the case of convergent evolution. The same Lawrence. Homology can be defined as in any resemblance between two species that can be explained by their common descent. He inverts the sign of the direction of implication. He defines homology by common descent. Nobel Prize.
Affirming the consequence.
Affirming the consequence. You should know better. Huh? And Adolf Remane, I told you, he is the guy that wrote the ultimate treatise in homology, related it to homology in topology, in mathematics. It's beautiful work. He said, I'll not say the same quotation, one characteristic, one defining characteristic of the concept of analogy is its relation in the sense of either or with homology. They are mutually exclusive. What of course is wrong. Owen said it often is the case that analogous structures are also homologous in some aspects. But you come to this misguided conclusion if you invert the signs of implication, because of course divergence and convergence are mutually exclusive. If you invert the signs of implication, you come to the conclusion that homology and analogy are mutually exclusive. Shame on you guys. But if you open Wikipedia page, you find exactly those definitions of analogy and homology. So things are bad, and it's up to us logicians to fix the world. We are but somehow they realize that they are doing something wrong. This idea of analogy and homology being mutually exclusive isn't quite right. Lawrence at some point says, but there are, however, mixtures of the two, analogy and homology, that there exist similarities which are caused by both. They say they are mutually exclusive, and then he says, well, but we can have both, because we need it. So he understands that he's doing something wrong. He realized that he needs homology and analogy as complementary explanations, as complementary concepts. There are cases in which both are required to explain some phenomena. And complementarity is a concept that appears everywhere in modern science, in particular in quantum mechanics. It was introduced by Niels Bohr. And Niels Bohr was inspired to introduce the concept of complementarity because his father was a biologist studying exactly those phenomena and realizing that, little Niels, look how interesting, in biology there are those two concepts of analogy and homology that are understood as mutually exclusive, but they are in fact, sometimes they are both required to explain something. As a young boy born, he tells that in his memories. He learned that from his father, a biologist, and then he used that to introduce the concept of complementarity in physics. So you see that my relation between quantum mechanics and those concepts in biology is not a simple one, but it can be traced back historically. No? And there are also statistical fallacies that can be related to those logical fallacies. You, as a logician, I'm sure you understood very well the logical fallacies, but I will try to explain the statistical fallacies by relating them to the logical fallacies. When you test for analogies and homologies, statisticians, bad statisticians, often use something that's called a p-value. you learn this dreadful thing in every course of statistics, of introductory statistics. What's a p-value? It's a kind of fallacy where you invert the roles of parameters and observables in a statistical model. You want to know how true is a statement about the parameters, and you swap the roles of things and start to think how true are your observations. That means your observations are your observations. They cannot be more true or less true. But you start to invent a game and say, how often would I have observations that are more unlikely than the observations that I had if I pretend the hypothesis is true under certain conditions determined by the observations I did. Something that doesn't make sense. It's swapping the roles of the parameter space and the sample space.
Professor,
Yeah.
isn't that similar to maximum likelihood estimation?
Well, maximum likelihood estimation is an intermediate step that you do when you compute a p-value. Given your observation, you compute your maximum likelihood estimator or maximum likelihood constraint to the hypothesis, and then based on that, you compute your p-value. That's something that doesn't make sense at all. And God punishes people that make things that don't make sense. People that use p-values are plagued by many paradoxes. P-values have the great merit of being asymptotically consistent in a certain way. If you have many observations, when n grows to infinity, you come to conclusion. But like a teacher of statistics that I had once said, when you have infinite observations, you don't need statistics. You need Microsoft. What's the? You need a spreadsheet and plot like that. They are logically p-values are logically inconsistent. When you have a small number of observations, you can come to incoherent conclusions. For example, you can test hypothesis H1 and come to the conclusion that it's true, test hypothesis H2 and come to the conclusion that it's true, and test A1 or H2 and come to the conclusion that it's false, or the other way around. No? The thing is just inconsistent. It doesn't obey the likelihood principle. That's a basic principle of good inference and many other diseases that you get if you play with p-values. The orthodox Bayesian solution to this thing is Bayes factors. Bayes factors can work well in discrete models, but it goes amok in continuous models, especially if you test sharp hypotheses that are the hypotheses, they are most important ones, that are equational hypotheses used to state any theory in exact sciences. That's why they are called exact sciences, because they are built upon equational statements. Yeah? You get asymptotic inconsistency, the diseases of this kind. Between the diseases of this kind, we have something called Lindley paradox. For small number of observations, they can be incoherent. They fail to comply with the likelihood principle. You need ad hoc integration measures on the hypothesis. You need ad hoc artificial priors, and all kind of difficulties play here. What's the orthodox answer to this, to all those problems? Denial. Huh? It's a psychological reaction, easy to understand. You say, well, I didn't like to test this kind of hypothesis. Anyway, this kind of hypothesis is ill-formulated.
Like I don't know and I don't like.
I don't know it, and I don't like it. And the physicists that formulate those theories, they don't know what they are doing. They are formulating theories that are bad theories. Yeah? Because they are equational theories. Yeah. Those are bad hypotheses. People that actually do science don't know anything about science. Yeah? Yeah, you can go this way, but I don't recommend. I don't recommend it. And what we do, is there a way to fix it? To fix all the problems? Yes, there is. The e-value and the full Bayesian significance test, the e-value of the epistemic value of a hypothesis given, of a hypothesis H, given observation X, is a statistical measure that gives you a support for sharp hypothesis that works perfectly well. It solves all the problems. It solves the classical problem of induction. It solves all the problems that p-values and Bayes factors have, but at a cost. At a cost, what's the cost? The cost is complementarity. Probability, it is one fundamental canon of statistical theory in the 20th century is that probability is the only calculus that we should use to deal with uncertainty. And the e-value uses in a complementary way more than one such calculus. You several calculi, all in the framework of abstract belief calculus. For example, it starts with a standard Bayesian model where you use observation to build a measure that's the posterior probability measure. I don't have time to explain to you what it is, but if you know the basic structure of Bayesian statistics, you know that you translate all the information that you gather from observations into a probability function. But then if you want to use that measure to compute the probability of a sharp hypothesis, it's zero. So that cannot be the appropriate measure. Indeed, in the e-value, first step, you translate this posterior probability measure into a posterior possibility measure. A possibility measure is another kind of measure that obeys different rules of calculus. And from that measure, you compute a measure of belief in your hypothesis. And that works very well. You can also use, well, at the end, you want to give a final, in many situations, you want to give a final decision. I believe the hypothesis, I reject the hypothesis. Some statisticians want to use a two-valued logic, 0 and 1, a Boolean, but that's not possible. We prove that that's not possible. You need at least a three-valued logic. Your decisions have to be accept, reject, or remain undecided. In statistics, remaining undecided in the jargon of statistics, they say to remain agnostic. You represented by a three-valued logic, so it's a third logical formalism, a third abstract belief calculus that you can use, that you need to use in this framework. And finally, it's possible to use paraconsistent logic to make sensitivity analysis of your measurements, or your experiments. So in this scenario, you are making use in a complementary and concomitant way of several abstract belief calculi. That's the price you have to pay to get coherence and between logic and probability. But that's the way to go. Okay? And in this framework, you can find strong support for sharp statistical hypotheses. Giving a firm epistemic grounding for ontology based on the theories of exact sciences and a firm epistemological grounding for analogy arguments based on prototypes and fine-tuning conditions. Although those are the big prizes that you get for going this way. Well, I think I have a little bit of time.
Can you give an example where an e-value can, with success, substitute an e-value?
Everywhere.
Like a simple example.
Everywhere. Well, I don't have time to roll the presentation, but in that presentation that I gave in Buenos Aires, I gave a very simple example of Hardy-Weinberg equilibrium law.
You said, you should better explain that. This homogeneous population hypothesis. Right?
It's a very simple example that you can draw. You can see in 3D space. You can make a beautiful picture, easy to understand. A theory that everybody knows because it's required study in high school. Mendel law and genetic equilibria. Hardy-Weinberg equilibrium is high school material, and everything works fine if you compute e-values, and not so fine if you want to compute base factors or e-values.
Leads to examples of problems in justice, etc.
We have hundreds of. There is one paper that is going to be published in a book for the 7th anniversary of Walter Camilleri, where we describe, give a very didactic description of the p-value and the full Bayesian significance set, and list almost 200 published articles that are applications for this methodology, applications done by real scientists that well, I'm sure they don't. That was not the first methodology they tried. First they tried p-values or base factors or anything that was already coded and available for them, and they realized that it doesn't work. And well, let's try something else, see if it works, and it worked and solve that problem. So it's not just a theory that has nice theoretical properties, but it proved itself worthy in the battlefield in the battlefields of science as a valuable tool for empirical science. So it's growing, it's expanding. So.
Could you make that paper available, the survey paper?
Yes,
That'd be
it's
great.
in my page. If you go to my page, there is a topic articles. The first article is this one. So let me talk a little bit about abstract belief calculi. Abstract belief calculi. The definition of abstract belief calculi follows the steps that Brandon used yesterday to define probability. You have a support structure that is defined basically by a sum. A sum is the core of the entire thing. and a scaling operation or a multiplication. If you have disjunct statements, the support you give to A or B is the summation of the support for A and the support of B.
I think you're on, are you on this slide?
Oops, again. And what the summation is depends on the particular belief calculus that you are using. And the scaling of the product works for conditionalization. The support of A and B is the support of B given A times the support of A. Now some examples.
Can you deduce the minimality condition from this equation?
Let me just go back here because so let me just first give some examples. In probability, we work in the support is in the continuous interval 0, 1. The summation is the arithmetic sum. The product is the arithmetic product. The minimum value, the no support value is 0. The full support value is 1. In three-valued logic, the image of the support function is 0, half, and 1. And the summation is the maximum operator. The product is the minimum operator. And that's it. Possibility calculus is something that's half the way between probability and either three-valued logic or classical logic. The summation is the maximum, like in logic, and the product is the arithmetic product, like in probability. And then you have two crazy belief calculi at the bottom just for you to play. The disbelief calculus, the possible support values are discrete 0, 1 to infinite. The summation is the minimum. The product is the sum, is the arithmetic sum. And the greater the value, the more your disbelief, the lesser your belief in the function. The last one is the improbability calculus. I will not read the definition. So, but the price that you have to pay to use the e-value in the Fulgation significance test is that you have to use the first three belief calculi in harmony. You have to use probability, possibility calculus, and three-valued logic. That's the price to pay.
Possibility in the sense of Didier Descartes.
Oh, those guys have a ton of papers in this.
Yeah.
In
They
this.
sort of open the area, right? I mean, based on Zadest theory.
I'm not sure if you say to those guys they base their work on their work, they get mad. They get mad. They invented it before. I don't know. But this general definition of abstract belief calculus is due to Darwish and Ginsberg, Pradé and Dubois Prade and Dubois are published a lot in this field. They have a
Industry,
índice de citação,
quotation
quotation
index.
index of 1,000, an H index over 1,000. It's a very good industry. But they have they have very nice papers too. This paper of Dubois and Prado of 1982 is a paper that I used very heavily to define object structure. It's a very simple paper. One of the original papers was written in a very simple way, very clear way. I love this paper. So, if you want to learn more about E-value and FBST, there are several papers that explore all the mathematical aspects of it. If you want to read one, you read the last one. That is the first paper in my page, the articles in my page. It's in archive. It's going to be published in Walter book as soon as Abilio
This year.
sends the book to Springer.
To the editors.
To the.
He'll be here tomorrow. We can.
Are you complaining? Oh no, that's why he's only coming tomorrow because he knows that.
He wants to avoid you. He wants to avoid you. Yeah.
And here, several papers about the epistemological consequences about the statistical methodology. If you want to, many of them are kind of speculative and maybe not so easy to read, but two papers I wrote trying to be more didactic. One of them is in the Logic Journal of the EGPL. In 1917, continuous versions of hard puzzles, also available in my webpage, and the other one is the sharper image, the quest of science and the recursive production of objective realities. What's an objective reality? Is a reality that I can check. The equations that describe it, I can check using this methodology and know the value of my fundamental constants with absurd precision. That reality that I describe under these conditions deserve to be called objective and deserve my ontological commitment. That's the best that I can do. So, how much time do I have? 35 minutes. Let me use let me briefly describe one case study, talk about the language of the honeybees. The language of the honeybees is being a source of endless debate in journals of biology, ethology, and in philosophy. How can we say that bees have a language? How can we say that they communicate? Isn't that something that is exclusively human, right? I will tell you, I think we can very appropriate say that bees have a language, and not only that, but a symbolic language, and they use it to communicate. Of course, saying that bees have a language is a metaphor. And the language of the honeybees itself is also a metaphoric language. So it's metaphor over a metaphor. Like any metaphor, Aristotle again tells me, to understand a metaphor always establishes a fundamental similarity, a fundamental equation, a fundamental way in which two things are the same. But understanding this, the metaphor also implies understanding that this similarity is not complete. Every metaphor has an axis of similarity and has an axis of dissimilarity or difference of discrepancy. So let's understand this metaphor. What is, in which sense this language is symbolic and useful to communicate information in the B world, and in which sense the metaphors that the B use and that we use, calling those language, the B language, a language, is incomplete. So, then bees speak dancing. They
TikTok as well.
Their dance is called the waggle dance. In Portuguese, dança do rebolado. The inside the hive, the bees dance something in the shape of an 8, like that, where they waggle in a given direction. This dance communicates two things: an angle and a distance. Inside when they dance, you have to measure the direction in which they waggle in relation to the vertical. And then the bees that see the dance go flying in the same angle in relation to the sun. So that's the direction they are supposed to fly. And the intensity of the waggle corresponds to the distance that they have to fly. And if they fly the right path, the right angle, to the right distance, they arrive at a very good source of food. And when the one bee finds a good source of food, she comes back to the sheep, because all the bees in the hive are female. Males in the beehive have a very short life. They are only used for the production, and then they are discarded. That's not a good thing to be a man in the bee world. Yeah? But so the bees are able to communicate with high precision what they want the systems to do. They are able to they do so purposefully. They have a purpose in mind, or I don't know if in mind. They have a clear purpose. The dance can be understood in a teleological way, in a purposive way. They are able to elicit action from the other bees. And if all that is true, we are more than justified to call that a language, and a symbolic language. Moreover, this language has a syntax, a clear syntax, and a clear semantics. They have distinctive elements: the waggle, the intensity of the waggle, the direction of the waggle, and a semantics, how that corresponds to reality. So in all those aspects, it's a language. No? And we can test that using statistical models, regressions. Regression models. Haldane was the first guy to do those studies, and he confirmed with very high precision that bees know what they are doing. So it would be very improbable that all the bees follow the instructions of the master bee to follow a given direction to collect pollen at a given distance. If that language didn't mean what it means. So again, we use an argument of improbability to verify, to give empirical support to our teleological statement. Huh? What else? There is a prototype. This is an analogical argument. There is a prototype for that analogy. The prototype that I use for that analogy is the language of vector algebra. Because honeybees are even smarter than what I told you. When it's windy, the bees give the instruction in a way so that the bee flies in a given direction relative to the sun. It compensates for the wind direction so that they arrive exactly what they have to arrive. So they do all the vector algebra inside their tiny brains to give their sisters exact instructions. So the prototype for this language, or for this metaphor, is vector algebra. And the fine-tuning conditions are all these vector operations work exactly as they should, so that the instructions take the bees exactly what they have to go. Let's not now talk about the dissimilarities, because the reaction against calling the bee language a language is huge. Some people are deeply offended when we say that bees have a language. It is something that people were deeply offended when Galileo said that, when Copernicus said that there is not the center of the universe. How come? We are the only animals that have a language. That's our distinctive feature. How can you say that bees have a language? Huh? So in which way are there dissimilarities between our language and the language of the bees? One perceived dissimilarity and one similarity that applies to some degree. That's why I have the interrogation mark here in the that's why I have the interrogation mark in the word dissimilarity. Is that the bee language is completely inherited, inborn and inherited. And our language is partially developed. Yeah? One thing that you can use to argue that our language is invented is that Portuguese and Hungarian and Hebrew are completely different languages. Yeah? But this similarity is not as strong, is not so clear-cut as you could think. First thing, these, although the basic syntax of the language is fixed, they do learn from experience. You watch the flight path of a very young bee and you see that's not so well adjusted. But the bee, with experience, with following her sisters, and she learns how to use the language that he was born knowing better and better. So She improves with experience. On the other hand, our language, although Hungarian and Portuguese appear to be very different, if you analyze those languages with care, you see they have a common algebraic core that is invariant. And that algebraic core that is invariant, well, there are many ways to describe it. One way of the Chomsky's way of generative grammars, that's not my favorite way. My favorite way is again with vector algebra, something more than vector algebra, with division algebras. You see that at the core of all human languages, there are division algebras. Division algebras is the algebras of reals, complex numbers, quaternions, and octonions. And you see very clearly that is so because our neurons, the neural network machinery that we use to process language is the same network that we use for fine manipulations. And fine manipulation is based on quaternion algebra. It's the algebra that describes translations and rotations in three-dimensional space. So this quaternion algebra somehow is at the core of all human languages. So we invent our languages, but don't invent them as much as you think, or many people think we do. So there are similarities, but they are not careful not to take them too far. What else? Intelligence. Some people say, well, we are intelligent. We use our language to do intelligent things. And the bees are dumb. They are pre-programmed and they cannot use the language to do anything intelligent. Well, maybe not individually, but there is such a thing called swarm intelligence. And bees and ants and other social insects are very intelligent if you look them not a single individuals, but as social organisms. There is a beautiful book of Bonador, Doringo, and I don't know how to pronounce the last name here. It's called Swarm Intelligence, that describes how those social insects use clever algorithms based on social interactions to solve very sophisticated problems. On the other hand, the science that we practice, we don't, like you said yesterday, we don't rediscover everything from scratch in our lives. We don't go testing every theory to believe it. Our knowledge relies very heavily in social knowledge, in testimony. So, in a way, our knowledge, our intelligence is also a swarm intelligence or a social intelligence. And there is a second book that has the same title, Swarm Intelligence, that describes exactly that, how our way of doing science is also in some respects a kind of swarm intelligence. And a related paper from a student of mine, I show how in genetic programming you can have an emergent semiotics coded in introns, not in exons. That is another form of intelligence. Silent. Third, the similarity, and that is with an exclamation point, because that's really a dissimilarity. We use our language to explain the world. Explaining the world to give explanations of how things are the way they do. The papers that have to do with that, the papers of Aristotle about this subject, how do we explain things, those papers have been collected in a book that has the title Metaphysics. Huh? Why this title? Because the guy that arranged the papers of Aristotle what said volume 3 is physics, volume 4 several papers of several subjects is the book that goes after physics. So I call this book Metaphysics. Huh? Volume 4. Huh? So metaphysics is this. Is the explaining how things are, giving explanations, giving causal explanations. Causal in Greek is idea, is just another word for explanation. This is metaphysics. And we use our language to explain things. For example, formulating theories. The best ones in equational form. And this is something that only we do. Let me end my presentation reading this quotation from Konrad Lorenz. For man who endeavors to master his habitat and its phenomena through insight into causal relations, the correct aggregation of stimuli emanating from things in his surrounding into objects of his environment is the basis of all knowledge and the highest requirement of life. So we explain how things are, and we see the world through these lenses, and the objects we see through the lenses of theory, of this theory, are the objects to which we are ontologically committed. That's what we do. That's our thing. Our human thing. For the animal, however, especially for the lower animal, who is essentially fitted to his habitat through inherited instinctual behavior, and to whom insight plays no role at all in his reaction to the stimuli of the environment, an objective comprehension of the environment is not an absolute biological necessity. So we too can live like animals if we choose without ever theorizing, but that's not a fully human life, I would argue. But don't worry, we humans theorize from birth. Another quotation from Lorenz: the a priori and axiomatic character of causal thinking find its equally convincing expression in the insatiable why of intelligent children. If you are parents, you know that at a certain age, your child doesn't stop asking why this, why that, why. That's he becoming human. My interpretation.
Gideon was calling the hell of a home.
Yeah.
Mr. White.
Have a room.
Hell of a home.
Okay, that's my point. Thank you.
Okay, so now we have about 15 minutes of questions. So anyone, Alonso, please.
Okay. At the beginning of the presentation, you were talking about evolutionary biology, Darwin's theory, and how probabilistic it is, and or how the probability began working in biology with Darwin. And I want to ask you, the same thing happened with Mendel, who was kind of contemporary. If you can tell us, in Mendel's genetics, to what extent uses a stochastic method, framework, and also when we talk about genes, and we can also draw these genetic trees, okay, from different generations, and to what extent we can say that there is analogy and homology when we talk about, for example, genetics in peas and human beings, because sometimes they didactically say that if we want to understand how genetics work in human beings, they use the classical example of peas, how peas are changed, okay, in different generations. And how can you say that that's analogy or homology? Just that.
Well, let me first answer the first part of your...
Was the question understandable?
Yes,
Okay.
at least the first part. I was already thinking about how to answer the first part. There is one article I wrote, where is this? In Sofia. Yeah, this article here. Carl Pearson and the Logic of Science, Renouncing Causal Understanding, the Bright and Inverted Spinozism. That article talks a lot about Mendel's work. And let me start answering your question, telling you that the entire project of 20th century statistics is a project invented by one man, that's Carl Pearson. And for him, there is nothing that he hated more than the last slide I put. There is nothing that would disagree more than my statement that the best that we do is to explain the world and to understand the world. He was a radical positivist. He was a positivist that thought that Comte and the logical positivists didn't start it being a positivist. He crafted the language of classical statistics so that anyone that uses classical statistics will be a positivist even without knowing it. In classical statistics, you never answer the question why. You never search for an explanation. You only test for a good fit. If a formula reasonably describes the result of an experiment, if it's a good predictive tool, talking about hypotheses, talking about explanations is forbidden. No? It's a sign of weakness, it's a sign of, in his word, mysticism. No? And so, why I mention that in relation to the work of Mendel? Because genetics is a mechanism that explains the laws of evolution, and he would have nothing to do with that. No? The story of Mendel is a very strange story because he was a friar at a monastery in Moravia, and he did his work because friars don't have much thing to do. and he published his results in the bulletin of the Moravian friars, and nobody read about it until decades later.
Yes. Next century.
Half a century later. Yes. No? But the problem that I used to answer Walter's question is exactly a problem that can be used to show that Mendel's explanation is the correct type of explanation, or at least as a strong empirical support for that mechanism. Either we are looking at a miracle, or the mechanism that Mendel proposes to explain hereditary is true. So
that's what I wanted to hear.
better go
That's what I
with
wanted to
Mendel.
hear. Okay.
Huh?
Mhm. Yeah, it's what I wanted to hear. How true is it?
No?
Uh-huh.
So, between believing in a miracle that has no explanation or making an ontological commitment to genes, I take the second alternative. And by the way, where those genes are, where this information is coded, is something that we only learn much later with the work of Watson and Crick and Rosalind Franklin. It was never recognized, but anyway, much later. So genes were latent entities. Latent is a word that statisticians love. Everything that lives in the parameter space is non-observable, is latent. Latent variables are metaphysical variables. So a statistical model has a world of observations, that's the sample space, and a second world, a world of variables that are explanatory. Those are the latent variables, the non-observable variables, the variables that explain the mechanisms behind the statistical model. So if they are the explanatory variables, they are the metaphysical variables. And statisticians are excellent metaphysicians, even if they don't know it. Why? Because in statistics, you always write latent variables with Greek letters and observable variables with Latin letters. So statisticians know very, very well what's a metaphysical entity, what's an observational entity. The ones that they work with Greek letters and the ones who work with Latin letters. And sometimes I ask statisticians, what do you think about metaphysics? He said, what? No, of course you know everything about it. You use it every day. You know intuitively what you are doing. You know exactly when you use a Greek letter or a Latin letter. You are a born metaphysician. You just don't know it. Well,
Okay.
some things about your question. I don't know if...
Yeah, sure. And the second question actually was, if I can condense it, and do homology and analogy work in genetics the same way as they do in evolution, as you were mentioning?
I think so. I don't know why not. They can work in many contexts. No? For example, analogy arguments can work, I believe, very well in models using reaction networks to see how a reaction, a chain of reaction, of chemical reaction networks is well calibrated, is optimally calibrated to deal with a metabolic problem. I'm searching for a biochemist to apply this tool. Didn't find one yet, but maybe we'll go to the biochemical department conform.
Thank you.
Okay, so Mike, you have a question?
In face of the topological aspects you have talked about, could we think in terms of connectedness instead of convexity? Because I think connectedness could express some more things than convexity in the context you are dealing with.
Yeah, the concept of homology has to do with connectedness. It has to do with what in topology is called algebraic topology. The concept of probability as a convexification, the convexification operator has to do with the nature of the topological nature of the continuum that has to do with convexity, separation theorems, and things like this, and things like that. Yeah? what's the structure of the open balls, what's the topological basis of what kind of structure you want for the open sets of your bases, this kind of stuff. The nature of the continuum that you have, the nature of the set theoretic topological space. And there are different questions.
Okay, we have about 2 minutes for a quick question.
Yeah, it's about the analogy and the notion of function. And so I saw the example, but I was interested since the beginning, like what is the role of the environment concerning the function, and how actually the function relates to that, and whether in the analogy I should take the context into considerations. And the example of the bees kind of reinforced this wonder of mine. And so yeah.
Yeah, baseball. Baseball is my favorite sport to watch because I know for sure that how you call the guy with the bat?
Hitter.
The hitter. I know that the hitter is acting teleologically. Right? He has the ball is flying with a heavily random flight path. The guy that throws the ball tries to make the life of the hitter as difficult as he can, throwing the ball with effects, with strange effects, and there is wind and the environment, and with all that the hitter hits the ball exactly in the middle of the ball, so that he flies an optimum path. When he hits the ball, he's performing the red equality signs. And then I cheer, teleological action. Huh? And that action has probability 0 of happening just by chance. Huh? The hitter knows what he is doing. His intent is clear. Otherwise, I would have a 0 probability paradox. That's why baseball is my favorite game. In no other sport, these conditions are so clearly displayed.
Yeah, even the best hitters only 25 to 30%.
Yes, it's a hard game. Having a purposeful action in baseball is not easy. Only the best can do it.
Mm-hmm.
But they can. The good ones can.
So for instance, like if in the future, like a honeybee, like a family of honeybees just changes the role and the function of the dance, and it's not just for giving directions to some food, but eventually it's just as a mating purpose. Like I don't know, it develops this kind of changes the function of the behavior because it doesn't need that function anymore, and so will it be still the same function, or since like the teleology is actually different, then the whole function of the behavior actually changes? Like to which level of abstraction I need to think about it?
I don't have time to find the paper, but in the slides there is a reference of how the bee dance evolves with different species to be optimally adapted to the environment. Bees, the code that is used to translate distance into waggles depends on the environment, how far the bees usually have to fly. The code is optimized. The angle of the dance mechanism is optimized according to the capacity of the bee seeing polarized light. And some bee species live in environments, the honeybees find most of their food at the floor. But some honeybees live in forests where the altitude of the food source is also relevant. So their species then also encodes information about height. So the language evolves, but it does not evolve ontogenetically, it evolves phylogenetically. And that's the difference. It doesn't evolve in one generation,
Yeah.
it evolves for the species.
And it will still count as the same function, like of the function of the answer.
You can trace, you can make an evolutionary
Right.
tree of the language,
Uh-huh.
of the B language, the same way you can make an evolutionary tree
Of species.
of the species. And in the same way you can make an evolutionary tree of human languages. There is one big branch of Indo-European languages, there is one big branch of Semitic languages. There is one big branch of Sino-Tibetan languages. And they look very similar to phylogenetic trees of biological evolution. And the tools that specialists use to trace, to reassemble those trees, are the same, exactly the same.
Okay, so we are out of time. Let's thank Julius.
Thank you very much for your attention, for your questions.
Thank you.
And we are back at 2.